All right, let's take a quick look at banked turns compared to flat turns. So we've already dealt with some problems where there's a car turning around a flat circle. So this would be like in a parking lot somewhere, just a nice level surface. And for the car to turn, friction force is responsible for the Fuch. So there's friction pointing towards the center of the turn. And when you add the arrows together, you get an unbalanced force that way. But there are some other situations where it's not friction providing the unbalanced central force, but something else. So take a look at this video here. This is taken at the Daytona International Speedway. It's a famous racetrack in the U.S. in the South. And these guys are standing on one of the turns. And so you can get an idea of just how steep the angle of the road is there. I think it's 31 degrees at this point in the turn. So there's people standing on level ground. And yeah, you can get a sense of what that looks like. Stop. Here's another example. This is from Germany. This is on the Nürburgring. But you can see how they've incorporated a little bit of banking there at the apex of the turn, and that's to assist the cars in getting around the corner. And what it does, you can see how it kind of tilts. Cars are so loud. You can see how it kind of tilts the cars towards the inside of the turn. Okay, and you can see how it kind of tips the car towards the inside of the turn. You can see how compressed the shock absorbers are on this side too. All right, and so the reason for that, if you look at it head on, so if the car is coming at you, here's the tires, car, little headlight action there, right? There's a driver. All right, so if the car's coming at you, clearly you're going to have gravity pointing straight down. But then the smoosh poosh is going to be perpendicular to the surface, so that's going to be directed something like that. And again, you saw in that one clip how compressed the springs, the suspension of the car was as it was going around the corner. So this smoosh poosh is going to be a little bit greater than it would be on flat ground, okay? And you can see that when I add the gravity to the end of this smoosh poosh, if it's just those two forces that we're looking at here, if there's no friction in this axis, that's going to result in an unbalanced central force pointing towards the center of the turn. So it's not relying on friction to turn, it's relying on the fact that the smoosh poosh is a little bit tipped in towards the center. And that's creating that FU. If the car doesn't go fast enough, I couldn't find a video of this, but if a car doesn't go fast enough, it could slide down that track towards the inside. And that's probably easiest to see in like bobsled races. If they don't maintain enough speed into the turn, they won't be able to stay up high enough on the banking and they'll slide into the inner wall. If they go too fast through the turn, they'll slide towards the outside wall. But if they have it at just the right speed, they can go around this corner without friction helping to turn. So now we got to think about how do all these angles go together. So you've got the angle of the incline here, theta. And if you look at how this matches up over here, this angle is going to be theta. So this angle is going to be theta. And since that smoosh poosh is 90 degrees to the surface, that means that this angle in here is going to be 90 minus theta. The Fuch is horizontal, so the Fuch and the FG are 90 degrees. And so that's a roundabout way of arguing for this angle up here being theta. So that angle is the same as that angle, is the same as that angle. So in looking at how these things relate to each other, the hypotenuse here is the smoosh poosh. The Fuch is the thing that we might might want to be solving for here. And tan theta equals opposite over adjacent. So in this case, the tangent of the angle of the embankment is going to equal the unbalanced central force divided by gravitational force. And again, you're going to calculate that gravitational force by taking m times g. So mg tan theta equals the Fuch, but again, that's for banked tracks with no friction. All right. Did I spell friction correctly? Cripes. All right. And we'll do another video that deals with what happens when there is friction.